In this video, we're going to take a look at water and its properties. So the most common way which we find water is in the liquid state. And this is because it's made up of those two hydrogens and one oxygen. And then there's two lone pairs of electrons on that oxygen, creating a 105 bond angle. There also is that very polar bond between the oxygen and the hydrogen, making water a very polar molecule. And because it's so polar, that negative side of the oxygen with the positive side of the hydrogens creates a lot of interesting properties that are unexpected for water. One of those being the large surface tension that water has, and the other, how low a vapor pressure water has. And that is directly related to the fact that it has those strong intermolecular attractions, the hydrogen bonding between those water molecules. They are so attracted to each other, you end up getting a much larger surface tension and lower vapor pressure than you would expect. So that surface tension is the inward pulling on the surface of water as those hydrogen bonds are attracted between those water molecules, holding them together tightly, pulling them in a spherical kind of shape for a water droplet because of how it's going to limit the amount of surface area that it has. This kind of acts like a thin skin. That's why when you do like a belly flop into a pool, why you get that really painful burn, because as you try and work your way through the water, you got to pull apart those water molecules from each other, and they are very cohesive because of how polar the water molecule is. In order to pull them apart from each other, it takes a lot of force. Every liquid has a surface tension, but again, water has a much higher one, especially much higher than you'd expect for the makeup that water has between those two hydrogens and that one oxygen. But again, because of those two non-bonded pairs of electrons and how polar that oxygen-hydrogen bond is, it gives it a much greater surface tension than one would expect. You can break apart this surface tension by adding in a surfactant. A surfactant is a substance that gets in between and it interferes with those hydrogen bonds, breaking apart those water molecules from each other. It's also called a wetting agent. So when you add in like a detergent to water, it actually breaks up those water molecules into smaller little pieces and separates them from each other, making it more wet, able to then be absorbed into a material much more easily. Also, that vapor pressure, as we discussed, is much lower than we'd expect because of those hydrogen bonds. Because the cohesiveness between the water molecules, those hydrogen bonds holding those water molecules together, prevents them from being able to jump off and evaporate off, creating more water vapor, creating more water vapor pressure. And it's a good thing, because if it weren't for that, we'd be in big trouble. Water being so attracted to itself, again, prevents it from evaporating too quickly, and then we'd have oceans and lakes just evaporating away really fast. The moisture in our skin would evaporate really fast and would be a lot more difficult to stay hydrated. We'll take a look at the reason why. Take a look here at this graph. We see all the group 6 hydrides, oxygen's family. As you work your way from bottom on up, we would expect the boiling point to then become lower and lower and lower based upon the fact that they all should be the same kind of relationship between those particles, the hydrogens with those group 6 atoms, and how they would share electrons and still make molecular compounds. But as they get heavier, they're moving more slowly, so that's why they have a greater boiling point, and therefore the lighter you get, you would have a lower boiling point, or oppositely where it would condensate, and you'd expect to see it as a liquid. So the hydrogen telluride down to the hydrogen selenide down to hydrogen sulfide, we see it decreasing, 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 because you need to get it even cooler to get it to be able to then crystallize with itself, or in this case be able to condensate with itself and combine and make a liquid. But water, we see its boiling point much, much higher than what we'd expect because of how strongly attracted those water molecules are for each other. Those hydrogen bonds need to be broken and pulled apart to now make singularly moving water molecules in the vapor state. So let's take a look at water when it's in the solid state, when water is ice. Most substances, as you cool them down, they move more slowly, therefore they become more dense because they take up less space. So their density increases. And then when they become a solid, they actually sink in that liquid because of that greater density. Water, oddly though, because of how it gets together with other water molecules when it's beginning to crystallize, actually takes up more space and has a lower density. So it does what it should do and what you'd expect as you get all the way down to 4 degrees Celsius. It does become more and more dense because they are moving more and more slowly, therefore using less space. However, at 4 degrees Celsius, they start to arrange themselves and how they're going to crystallize. And when they do that, they actually take up more space because they're going to make an open framework, kind of like a honeycomb. Where now they're actually taking up extra space as they crystallize and making this repeating hexagonal pattern in an open framework, and this density now decreases, hence why water floats. So here we see how that actual density changes. Starting from the right at 100 degrees Celsius, once we first condensate, as we cool it down from water vapor or steam, we do see that density increases as we'd expect as it gets cooler and cooler and cooler, moving more slowly. However, again, once you get to 4 degrees Celsius, you see that curve change and go back the other way, and water again gets less dense as it freezes and crystallizes and takes up more space, leaving that open framework of repeating hexagonal pattern. Water also needs a lot of energy to not only just change temperature, but to change its states. We know water, when you try and boil it, takes a really long time to boil because it takes a lot of energy to take that room temperature water of 25 degrees Celsius that's sitting in a pot and heat up to 100 to get it to boil. There's 4.184 joules of energy needed for every 1 gram of water to change that 1 degree Celsius. That's why it takes a really long time again for that water to get up to a boiling temperature, because it's a lot of water and a lot of energy needed to do that. There's even a greater amount of heat of fusion, the amount of energy needed to either crystallize water into ice, or energy needs to go in to take ice and melt it back down. There's 334 joules needed for every 1 gram of ice to change it into water. So to kind of put that in perspective, that's the same amount of energy needed to change the temperature of water, 1 gram of it, 80 degrees Celsius, the same amount to then melt it. So to get a better perspective of that, let's actually just watch how long it's going to take to get ice to melt relative to how quickly it's going to get up to a boil. So we have here 200 milliliters of water in a frozen block. And that 200 milliliters of water takes a long time for it to melt, but then here only a quick couple seconds before we get to a boil. And again, that's because of how much energy it takes to melt ice. That's why snow sticks around for so long in the winter, because it takes so much energy in order to get that snow to melt. So even on a 50-degree day where you think, oh, we're well above freezing, these ice piles should melt away really, really fast, but actually they hang around for quite a long time. If you go to a parking lot where they've put a whole lot of snow into big, large piles in one spot of the parking lot, it could be June before those big, large piles are gone, because of how much energy needs to be put into those snowbanks in order to get them to melt down and be completely washed away.